All right, hi everyone. My name is Saurya Das. I'm going to talk today about me and my folks who've joined me here are going to talk about operational best practices on Azure Kubernetes Service. So I work as a product manager in the Azure Kubernetes Service. I've been with the team since the day it was launched, and it was called Azure Container Services. With me, I have Mohammed Nofal and George Palma. They are architects in the Azure Global Black Belt team. I also have Andrew Randall. He's a guest speaker. He's the co-founder and the VP of Business Development at Tigera. So during this session, we're going to talk about our experiences with dealing with customers and working with them hand on hand over the last couple of years or so. This is a 300-level talk. It's pretty deep into Kubernetes. If you want some basic understanding of Kubernetes and overview, we have other sessions listed here that you can go to. And then what we are going to do is, we'll take questions at the end, or you can come by the AKS booth up there in the expo hall and you can ask me any questions you want. So in the agenda, we have primarily we'll talk about cluster isolation, how we manage how to manage resources in Kubernetes, what to do about networking, network policies, how do you secure your environment, how do you add auto-scaling, do you use the cluster autoscaler or Azure Container Instances to scale, how do you do logging and monitoring to ensure that your cluster is functioning properly. So let's get started, and I'll hand over to Mohammed to talk about cluster isolation. Thanks.
Thank you, Saurya. Okay. So yeah, my name is Mohammed, and I'm going to walk you through the cluster isolation and resource management and the networking sections. So one of the top questions that we get from our customers is, how many clusters should I have? And in this section, I'm going to try to give you some guidelines that will help you to take such a decision, right? In Kubernetes, there are two patterns for cluster isolation. The first pattern is the physical isolation. In this pattern, you dedicate cluster per team, per workload, per environment, such as in this example, you have a development cluster, you have another staging cluster, and then on production, you start dedicating clusters per team. So production team 1 and team 2, and so on. The other isolation pattern is the logical isolation pattern. And logical isolation pattern, you group workloads based on the environment, based on the sensitivity of the workload maybe, or based on the owner team, and so on. So in this example, I have two clusters. One cluster is for dev and staging, and I have two developer team workloads in this cluster, and I have a staging team in there. And in the production cluster, I have team 1 and team 2 and team 3, and so on. So how would we subdivide the cluster in order to make it like this, right? So we're going to use Kubernetes namespaces for this purpose. And for those who don't know, Kubernetes namespaces is a way to create virtual clusters within your cluster, or to subdivide your cluster. So the namespace will be our logical isolation boundary for the workloads. So now we have multiple workloads within the cluster, but what we need to make sure is we are safely isolating these workloads from each other. We don't need those workloads to gain access to other workloads, and we need to protect the workloads from each other, right? So Kubernetes has some features that will allow us to achieve this safe isolation. There are three domains that we need to think of. The first domain is the scheduling. In scheduling, we need to make sure that the cluster resources are protected, and we need to make sure that the pods are not contending for the cluster resources. This can be achieved using the resource quotas in Kubernetes, and this will be the focus of this section. Then the other domain is the networking. Networking in Kubernetes, in general, is a flat network, right? Which means that all pods and all namespaces, by default, have access to each other, right? By default, all pods in all namespaces have access to each other, and you don't need to do that, right? To prevent this from happening, you can implement network policies, and which Andrew will be discussing in depth in his section. Then you need to make sure that you're protecting the access to your API server. You need to make sure that only authenticated and authorized identities have access and can perform actions on your cluster. This can be accomplished using our backend pod security policies. And lastly, all of this that we did in the namespace, we still have to do the container level isolation, because we don't want to end up with a compromised container that will cause an elevated access to the node. So both authentication and authorization and cluster level container level isolation will be discussed by George in his section. So Kubernetes resource quotas, what are they? They are a way to implement limits on our clusters, right? The limits can be in two forms. The first form is compute limits. We can implement compute CPU limits and memory limits and disk limits and so on the namespace. The second form is objects limit. You can configure that your namespace will only allow 10 pods to be spun up in it, right? So that's the objects limit. Once you enable resource quotas in your namespace, any user who's trying to deploy a resource or a pod to this namespace, which with no resource quotas advertised in the pod definition, will be forbidden from deploying to the namespace, right? So now you get this for free. All users have to advertise limits on their pod in order for it to be deployed to the cluster. If they were not if they violated the quota, then they're going to get 403 forbidden, and they will be advised to go and apply resource limits. Lastly, Kubernetes will never overcommit. So the sum of your requests to your Kubernetes cluster should equal the sum of resources in the Kubernetes cluster, which means if you have a 10 gig of RAM available in your cluster, you cannot request more than that. There is no overcommit in Kubernetes, right? So now, what are the differences between physical and logical isolation? First, let's look at pod density. In logical isolation, you can dense more pods, because now you have more teams, more workloads, you have better visibility on your cluster, so you can dense more. In physical isolation, you're dedicating clusters per teams. There is a very good chance that you're going to end up with some underutilized resources, right? Not all the teams will be utilizing their clusters to the fullest. When it comes to the cost, physical isolation is higher cost than logical isolation because of the cost of the underutilized resources. From Kubernetes experience perspective, on logical isolation, you require more experience than physical isolation, because if you want to deploy anything to production, you have to make sure that from day one you have applied all the isolation and security controls required in order to safely isolate your workloads. While on physical isolation, you still have to apply all the security controls required, but you still have more time to do it, right? You can go production and then start applying the security controls in physical isolation. Because in physical isolation, you just have one workload contained in your cluster, not like 10 workloads, and the surface is not as big. From security perspective, both are high. The physical isolation has a better advantage over logical isolation in the sense that you're just exposing a smaller surface. You have one workload or one team inside this physical cluster. While in logical isolation, you have a bigger surface, which means that you can achieve high security, but you need to be more strict in your security controls applied to the cluster. Blast radius of changes. Again, in physical isolation, you have smaller surface. Thus, the blast radius of changes will just impact this workload. While on logical, you have a bigger surface, then the blast radius is bigger. Lastly, when it comes to management and operation, and this is a very interesting topic, right? In physical isolation, you can take the approach of you build it, you run it. So you hand over a Kubernetes cluster to the development team, and then this development team will manage this cluster. You can do that. On logical isolation on the other end, you have multiple teams in the same cluster. So thus, you have to think of either you have one single team managing the big clusters, or you're going to have a cross-functional team from all dev teams managing this cluster, right? So now we're going to do a small demo to show this how we can protect resources in the cluster. All right, cool. So I'm going to create a namespace. In this namespace, I'm going to apply this resource quota to it, right, with these limits. Then I'm going to try to deploy a pod that doesn't have resources. And if you notice this, if you're using VS Code with the Kubernetes plugin, you're getting a warning that you're not applying resource quotas on your pod definition now by default. Then we're going to see what's going to happen with this pod that doesn't conform to the policy that we have. Then I'm going to deploy a deployment that has resource limits already defined in it and see what's going to happen. So let's do B and get this up and clear. Right. So first, I'm going to create a namespace called Ignite. Right. Then I'm going to describe the namespace Ignite. If you can see here, we have no resource quotas and no resource limits already identified, right? So now I'm just going to change the namespace to Ignite to make it my default. Then I'm going to apply the resource limits to the Ignite namespace. If I describe the Ignite namespace again, now the namespace is tracking the quota, right? So I have the use versus the hard. So the hard is what I implemented. The use is what's being used now. So now I'm going to create the pod that doesn't have resource quotas applied to it. So this pod is forbidden from running into the cluster, and because it doesn't have limits on CPU and memory. Now if I apply the deployment that has resource limits to it, this should work. If we get the pods, all right. So we have 4 pods, 3 are creating 6 seconds ago. If I describe the namespace, now I have the namespace is tracking the usage already, and now the usage versus the hard is almost the same, right? So, and that's it for the resource quotas demo. It worked. Awesomeness. Right, so let's switch back to the presentation. So two quick things. There is a tool called Kube Advisor. It's an open source tool that we developed. One of our engineers did. You can run it. It's going to scan your cluster. And it's going to report back of any pod that doesn't have resource limits applied to it already, right? We spoke about the VS Code extension for Kubernetes. And this one, you can get alarm or get warnings that you're not applying resource quotas. So to summarize for the resource isolation, think of the sensitivity of your workload, the cost, the organizational culture, your operational model, the blast radius when trying to choose which isolation model that you're going to adopt. You pretty much can end up doing both, right? 80% logical isolation, 20% for the supercritical workloads are on physical isolation. And plenty of customers are taking this approach. So just think wisely of how you're going to apply this. Always use namespaces, even if you are on physical isolation, and never, ever use the default namespace for anything related to production. Last thing, apply resource quotas even on physical isolation, because you need to still protect the cluster resources from the pods, right? So that's it for the cluster isolation. Now we're moving on to the networking. In AKS, you have 2 modes for networking. The first mode is the basic networking mode. The basic networking mode is done using a network plugin called KubeNet. And KubeNet is a very simple network plugin that manages the network within the node. If you need cross-node connectivity, you need IP forwarding and user-defined routing, right? There are drawbacks of using this approach. The first drawback is you have 2 different IP siders to manage. Now, your nodes are on a network, on a subnet, and then your pods are on a different subnet. The second thing is you have a performance impact of this approach because of the IP forwarding. Third, peering and on-premise connectivity is a bit tricky, right? Because of the different subnet that the pods are residing in. The other mode in AKS is the advanced networking mode. The advanced networking mode is done using the Azure CNI, Container Network Interface. The CNI is a vendor-neutral protocol that is used by container runtime to attach and detach containers to the network providers. The Azure CNI itself is an implementation for this protocol that helps you integrate your Kubernetes cluster with the Azure Virtual Network. And there are advantages for this approach. The first advantage is now you're going to end up with a single IP CIDR to manage for both your pods and your and nodes. You're going to have better performance as your pods are directly attached to the VNet, so no IP forwarding. And finally, peering and on-premise connectivity is out of the box, right? So how does it look like when it comes to advanced networking? You have an AKS cluster and a subnet within your virtual network. Then if you want to connect to a backend database, for instance, oh, yeah, you can see this, like a SQL server, you can use the service endpoints. Using service endpoints, you make sure that the communication remains within the Azure backbone network. And you can, on the SQL node, you can configure restriction for the access just from the originating VNet, which is the AKS VNet. If you need to connect to other networks, you can just peer. And if you need to connect to on-premise, you can just use ExpressRoute or Azure VPN or any other means. Now, let's say that you have a web application, and you need to expose this web application to the internet. You're going to be using the Kubernetes Service API object, right? And to expose this to the public in Azure, you need to change the type of the service to load balancer. Once you do this, we're going to create an Azure load balancer for you in front of your cluster, and we're going to attach a front-end IP address. The front-end IP address can be either dynamic or static by using the load balancer IP parameter in your service pod manifest. If you create more services, we're going to keep one load balancer and then attach more front-end IP addresses to the load balancer. The traffic flow is from the internet. It's going to go to the public IP of the load balancer. The load balancer will forward the traffic to the nodes. Proxy within the nodes will snag the traffic and move it to the pods using round robin. So the load balancing within Kubernetes from the service is done using round robin, very simple round robin. Yeah, and one thing to note that the service object in Kubernetes supports layer 4 basic TCP, UDP use cases. So no SSL termination, no advanced routing, none of that. If you have an internal service that you want to expose to just other VNets or to on-premise only, you can use internal load balancer. All you need to do is in your pod manifest just to annotate with that they're requesting an internal load balancer. Azure, in turn, will provide you with an internal load balancer and provide you with a private IP address from your virtual network. Pretty much the traffic is the same flow. So now, what if we need more than layer 4 TCP, UDP load balancing? What if we need SSL termination? Kubernetes has an API object called ingress. The ingress is an API object to manage the external traffic to services in Kubernetes. Using ingress, as it stands today, it supports HTTP and HTTPS type traffic only. You can do path and subdomain routing. You can do SSL termination. And you're going to be saving on the public IPs on the Azure load balancer, because now you have the ingress as the single entry point for all your services in the cluster. For ingress to work, you need to have an ingress controller. The ingress controller is an application that listens to the ingress API and satisfies the requests that are hitting the ingress API. Right? There are plenty of ingress controllers out there. The most popular one being Nginx, and which is the one maintained by the Kubernetes community as well. So I have an example of ingress here. I have a domain, contuso.com. This domain needs to have SSL termination. And I have two services in this domain, /A and /B. If I'm hitting /A, I need to move to /A service. And if I'm hitting the /B, I need to move to the /B service. So I have this TLS parameter inside the ingress object, which is pointing to a secret that is the Contuso secret that is holding my TLS certificate. And then below, I'm defining the rules for if you're hitting the contours.com/A, go route the service to service A. And if you're hitting the B, route the service to service B. The traffic flow in this one is internet, Azure load balancer. Load balancer will move the traffic to the nodes. The ingress will take the traffic. The ingress controller will handle the traffic there. And then look inside the traffic where it's hitting. And then based on that, route the traffic to the service. And then the Kubernetes service will just round robin across the pods assigned to it. Right? Now, what if that's a public service, right? What if I need to expose an internal service? You can do that, but you need another ingress controller, right? The other ingress controller, you can just expose it as an internal load balancer, and then it's more or less the traffic flow is the same. But note, to use this, you need to start using the class parameter inside your ingress, because now we need to categorize which ingress controller handles which traffic or belongs to which service. So you can tag with the class resource that says that this service belongs to the public service, and then you can have another ingress object that says traffic hitting the linux.contours.com should go to the internal load balancer. Now, what if we need EWAF, a web application firewall, in front of our services? From AKS perspective, you still have your services fronted by an ingress controller. This ingress controller will be exposed and is an internal service, right? So it has an internal load balancer. It's no longer public. This internal load balancer will serve as a backend IP address for Azure Application Gateway. Azure Application Gateway lives in another VNet or just another subnet. You can peer the subnets, right? So the Azure Application Gateway will take the ingress or the internal load balancer as its backend. So the traffic flow will be from the internet. It's going to hit the Azure Application Gateway. Azure Application Gateway will route the traffic to the load balancer, and then from there, it's the same traffic as before. You can do SSL termination also on the web application firewall. And now you might be wondering, why should I use ingress if I'm using Azure Application Gateway? You might need it if you need to secure or encrypt the communication between the application gateway and the ingress, if you need SSL termination. So you can SSL terminate on the application gateway, then SSL terminate again on the ingress. Or you might need it if you need to offload the routing to the ingress. So you still route everything to the ingress, and ingress handles the routing to the different services within Kubernetes. Lastly, what if I need how would I manage the access to my nodes? I need to manage the nodes now. How would I manage the access? So you pretty much keep the same setup. You have a VNet for AKS, another VNet with management VNet. You have a subnet for a bastion host or a jump host. You manage the connectivity between this VNet and your on-premise. Your administrators will be accessing the bastion host, and from the bastion host, they will be accessing the AKS nodes. AKS nodes are by default on a private subnet, so they're not accessible from the outside. So this is why you need such an approach. Now, let's do a small demo on ingress. So what I have here is a cafe application. And this cafe application, oh, sorry, it's not. Repeat. What I have here is a cafe application. And in the cafe application, I have two deployments. I have coffee, and I have tea. The coffee has two replicas, and it has a service attached to it called coffee service. And the tea has 3 replicas, and it has tea service attached to it. Right? That's simple. It's cafe application serves tea or coffee. Right? If I hit the tea, I need to hit the tea service. If I hit the coffee, I need to hit the coffee service. I have a secret. The secret is holding my TLS certificate, right? A self-signed certificate, just for testing purposes. And here I have the ingress object itself. And the ingress object, I'm referencing the TLS certificate, which is cafe secret. And then this domain, cafe.linux-joe.com, is mine. So if you hit cafe.linux-joe.com/t, go to the T service. And if you're hitting the /coffee, go to the coffee service. So let's get this done. Right. So just switching to the default namespace. I already have an ingress created, just to save time. So I have an ingress one. I already exposed the ingress to a public load balancer. So the ingress has already an external IP address. Now I'm going to create my application. Then I'm going to just make sure that my application is working. So I have both deployments, T and service, available 2 and 3, which is good. Get the service. Now, note here that the services are not exposed to the public. Services are now just available only within the cluster. I don't have an external IP for the services, right? So using this approach, using ingress, you're going to save on the public IPs. The services are just exposed to the ingress controller itself. So I'm just going to apply the secret, then create the ingress object. Right? I already pre-created the IP address to point to my domain. So dig, yeah, it's there. So now if I curl the /t, I'm going to get 1. Right? So that's the first pod. If I curl again, that's the second one, because I have 3 replicas in T, right? Okay, one more time. I'm going to have the third one, right? So ingress moves the traffic to the service. The service will just do round robin, and that's just round robin. Like 3 replicas, round robin, 1, 2, 3. If I hit the coffee, then it should be more or less the same, right? And yes, that's it. Ooh. And 5. Okay. Just to summarize, use AKS Advanced Networking for seamless integration with your VNet and to have all the advanced use cases of interconnecting with other VNets and to on-premise and so on. Use ingress controllers for HTTP and HTTPS type traffic. For any other type traffic, you're going to use normal service object in Kubernetes. If you need a WAF, you can use either Azure Application Gateway. By the way, we introduced an ingress controller for Azure Application Gateway last week. So now you can automate the process of creating the connector to the Azure Application Gateway. Go check this out. If you need a different WAF, you can use like Trafic. You can use anything from the marketplace, like 5.5, Barracuda, and so on. And lastly, use Bastion host. So what's documented is like you can SSH to a pod, and then from the pod SSH to the nodes. Don't use this for production. Use a Bastion host for production. Yeah, and this would be it. So now I'm going to hand over to Andrew, who's going to discuss the network policies. Right.
Thanks, Mohammed.
Sure.
So we're going to talk about network security and network policies. And there's a reason why this is a really hot topic when you start talking about dynamically orchestrated containers. So there's a great thing about moving to this dynamically orchestrated environment, such as AKS, is you get very agile deployment of services, the kind of things that you were just seeing there, dynamic creation and destruction of pods as demand requires it. And we see a very high density of containers and much shorter lifetimes as a result. These are numbers that are actually out of real-world surveys of how people are deploying containers. Now, the flip side of this is that you have new security requirements come in, because if you do the math on this, you're seeing changes at a network level of workloads of 300-400 times the kind of rate that you had in a much more static virtual machine kind of environment. And the traditional approaches to network security don't translate into this world. So we've had to really think from the ground up about a lot of the approaches to security at the network layer. And some of the best practices that we're seeing people adopt, I'll go through. There's really kind of goes into 4 areas. And the first is to realize that the traditional approach to network security, which has been to apply a perimeter firewall to a secure area, doesn't really apply in this world. So whether that's a virtual firewall or a network security group that's protecting the outside of your cluster, that's great. Don't take that away. But you also need to think about how do I apply policies that define the connectivity between the pods within my cluster, and whether that's protecting at a namespace level or at a finer-grained level to really defend against attacks from inside the cluster. And a couple of ways that we see people doing this. One is to say, as part of my development flow, as part of the CI/CD process that I'm introducing for defining and creating new microservices, it becomes part of the developer's job to define what workloads it needs to access and what services are going to be accessing it. So that's one approach. The other is, particularly if you're looking at a lift and shift kind of model, where you're taking legacy workloads and bringing those into containers, you probably don't know what connectivity requirements they have. So you need to do some monitoring to baseline the base traffic patterns and then turn those into policies. The next thing that we're seeing is really kind of going a level beyond the basic policy rules to really embrace a model that's becoming known as zero trust network security. Now, that sounds like a bit of a buzzword, but there is some real technology behind it, and really it's embracing this approach that we can't trust the underlying network. We can't assume that just because 2 workloads are in the same network zone that network connectivity can be allowed. And there's a couple of aspects to this. So the first is multi-factor authentication. So in the same way that when you log onto your bank account, you have to get your password and also maybe answer some other questions. We want the same kind of thing for pods. If a pod is going to access another pod, then it has to identify itself, not just via its network identity, but also prove that it's got the right certificate for a TLS connection. And we want to define policies that put these together and check both of these identities at the same time. And then on top of that, we want to encrypt all of our data in transit because we don't want to be able to open up to exploits from the network. The next thing we see, if you see the kind of very rapid changes in the environment, is that the kind of approach you've had to compliance, where twice a year perhaps, and a compliance audit officer would come in and check out how your VMs are connected and the firewall setups, and it all looked good, and they go away and they come back 6 months later. That no longer works because things are changing so fast. It has to be continuous. So you need continuous visibility, continuous monitoring, reporting against the kind of compliance regulations. And then lastly, this is kind of a subtle one, and it comes out of the idea that Kubernetes, if you look at the origins of Kubernetes, it really started as a kind of a developer-first environment, and a lot of the concepts work great for developers, and we've added a lot of layers on top of that around how enterprises work. So enterprises typically don't just have one team. They'll have a compliance team, a security team, a network ops team. They'll have different business units, different application teams within each business unit. And so we're seeing the best practice here in terms of how you manage policies and the network policies around those organizational units is to structure them into hierarchical groups with RBAC controls on those policies and managing them, because a policy is just a YAML object in Kubernetes. Treat that just like code and integrate that into a CI/CD process with approval steps and verification before you push it into deployment. And so this is, we're starting to see this approach to network policy and integrating it into the pipeline. So I've talked quite a bit here about this term network policy, and really this is a foundational technology for all of the network security you're going to see in Kubernetes. And it's got really these key characteristics. So it's built as an API within Kubernetes, and because it is a Kubernetes native API, it leverages a lot of core Kubernetes concepts. So it leverages labels. So identifying which pods a policy should apply to is defined by a label selector. Identifying which pods they connect to is defined by another label selector. It's declarative. This is, again, a Kubernetes paradigm. We just state what is the connectivity that we want to happen based on these label expressions. And the controller, the network policy controller, goes away and makes it so. You don't have to worry about updating it as pods come and go. And that leads me to the third point, which is this is super dynamic. So you need, any time a label gets updated or any time a pod is created or destroyed, any of those events can result in recalculation of all of these micro-segmentation rules across the entire cluster. And that has to happen in milliseconds, because otherwise you're not going to be protected in real time, which is what obviously we're after. So these are the concepts in network policy. As I say, it is a Kubernetes API. However, Kubernetes itself doesn't have an upstream implementation of that API. Kubernetes just says, here's the API, and because there are different technologies for networking, you have to have a plugin for network policy. So this is where Tigera comes in. We actually developed the reference implementation of this API. It's an own open source project called Calico, deployed in all of the major Kubernetes environments. And we've been working a lot with Microsoft recently, both to, it obviously it started on Linux like Kubernetes, but to port it to Windows, and also working with Saria and the AKS team to bring this into AKS as well. So this is coming to AKS. And the bottom line here is the security stack that you need here is going to be built on Azure CNI. That's the advanced networking that Mohammed was talking about, putting Calico on top as the security technology. And then we have some commercial products called Tigera Secure, which give you all of those enterprise controls, visibility, compliance, the kind of things that I was talking about earlier as best practice. So I'm going to just take a quick look at a demo here and show you what this looks like. So in the interest of time, I'm going to make this super quick. So I've got a cluster here running 4 pods. As you can see, they're all web server pods, and I can access them because it's an open cluster. So what's that address? I'll take that address. So as you can see, it's returning it now. So I'm going to show you a network policy. This is what it looks like. It's an API object. If you're familiar with Kubernetes YAML, this will look very familiar to you. So the spec of the object has a pod selector. So we're going to match anything where the label app equals IIS. And this is a pretty severe policy because it's saying I'm not going to let anything have access into here. Now, where I've got those just empty brackets there, that could equally be a label selector to restrict access to certain nodes. And in this case, we're just going to block access to everything. So I'm going to apply it. And if we see, so I've applied that policy. Now, if I get net policy, you'll see that it's there, and it shows me what the policy name is no IIS. It selects that, and if I do my curl command again, now I see it times out because the network policy is in place. So that was just a demonstration of how network policy enables you to control access to pods. And in this case, you'll see eagle eye among you will have noticed that IIS pod is running on Windows. We're showing the Calico on Windows here. So this obviously is not running on AKS. This is my own Kubernetes cluster. But I just wanted to show you both of those capabilities. OK. Thank you. I'm going to hand over here to George to continue.
Change it. Yeah. All right. So now for the fun part, right? So security. So no one really wants to have your sensitive information being accessed by anyone and everyone, or having your cluster compromised, or having an attacker gaining privileged access to it, or even internally having your users doing unvetted actions or accessing unvetted content, running unvetted software. But normally we see security kind of come as last, and only when a problem comes up. Normally sometimes due to complexity, sometimes due to how cumbersome it can be. So hopefully with this section here, we want to talk a bit about how we can make things easier, some of the, this is by no means comprehensive, but some of the best practices we've been seeing, and how AKS can also help things become a little easier for you. So diving right in, the first thing you need to worry about, of course, is your cluster as a whole and the cluster security part. So the first and foremost object that you really want to protect is, of course, your API server, the place where you actually run commands like kubectl or kubectl create, list, etc., where you actually do tasks against. And how you actually secure that, where there's two ways. The first one, of course, is authentication. Make sure that you authenticate and are an authenticated entity before you actually do a request. And the second one, authorization. Make sure that you have the right permissions to do that task before it's actually executed. So this is done normally by an authentication provider in conjunction with Kubernetes role-based access control that can very fine-tune, define what you're authorized to do and what you're not authorized to do. Azure provides a very, very nice integration with Azure Active Directory and Kubernetes to take care of that first part, the identity part, and make sure that your users in your Active Directory can log into Kubernetes and only perform the tasks and the jobs that they have access to. And with Kubernetes RBAC, you can give them that minimum permission required for them to actually operate on those tasks. So how does that really look like? Well, if you're a developer today and you want to do something like kubectl create pod, you'll be prompted basically to actually log in against AD first and foremost. After you actually log in, you're going to receive a token back, and you're going to use that token to issue that request, that kubectl create pod, against the Kubernetes API server. Kubernetes, on its turn, is going to say, OK, let me get that token and validate you. Let me get the groups, the AD groups that you were part of. And based on that, it's going to apply the role-based access control policies and see, OK, you're part of a group that is, has permissions to do that task, or you as a user have permission to do that task, and return it, or it's going to deny your request. But how can you actually set this up, and how easy it is to set up? I told you it's easy. How easy it is? Well, first and foremost, you're just going to need to create an identity, what we call an Azure AD app, that you're then going to use to link your Kubernetes cluster and establish a relationship of trust between your Kubernetes cluster and your Azure AD. After you create that app, you're basically going to run the simple command that you normally would do, the AKS create, to create a Kubernetes cluster. AKS comes with RBAC enabled by default, so that part's covered for you. And then you just need to reference that app, that identity that I just mentioned, that is going to establish that relationship of trust. After that is done, wait a minute, what about configuring RBAC? Who's going to do that? If I create a cluster that already has AD enabled, who's going to configure RBAC? Well, that normally would be the administrator. The administrator is going to pull the kubeconfig with that ---- admin tag. That is basically a God mode kubeconfig that will give you access to immediately run commands against the cluster. And after you immediately run some commands, you can, of course, do the important things that you need to do now, which is actually create some roles, like in this case, a cluster admin cluster role, and then bind those roles to particular users, like in the first example, or to groups, like app development team 1. After that is done, then the users are actually able to do the flow that you just saw. So as a recap, the Kubernetes administrator is going to log in for the first time, is going to download the admin kubeconfig file, is going to access Kubernetes and make those configurations. And then finally, it's going to enable the flow that you did, because the developer is now able to go and download the normal, non-privileged kubeconfig, and it will be prompted to access. Now you might be asking, wait a minute, doesn't the developer then, if he knows, just going to download the admin kubeconfig and that's it? Well, that's where Azure RBAC comes in. In order to download that kubeconfig, you need to use your identity against the Azure portal and the Azure API to actually download the corresponding kubeconfig. And both of them have different roles, of course. So while your admin might be a service cluster admin and is able to pull that admin kubeconfig, your users, they are only able to pull a normal kubeconfig that will then make them authenticate against AD for every request that they do. So how does that look like? So the developer will just use the AKS get credentials, but without the ---- admin flag. If they use that flag, they're going to get the denied request, of course. They'll try to do any type of command, like get nodes. They'll be prompted to log in. They'll log in. And if then their user or their groups have permissions to, for example, do this type of cluster listing, they'll get a request. Otherwise, they'll get an error forbidden. So this is the first thing that AKS really makes simple for you, is how to actually take care of authentication and authorization. Now there is a different type of authorization that Kubernetes supports that is handled through admission controllers. Admission controllers are basically, in a simple way, pieces of code that intercept the calls made to the API server and then run some specific policies against it. There are many, many admission controllers out there, some in alpha, some in beta, some more stable, and we definitely don't have time to call them out all. They all have their own features. I called out a couple of them that I find are very relevant and used quite broadly. First one is deny escalation exec. So what this does is, everyone here probably has done a kubectl exec into a pod, right? What this prevents is that after you do that, you try to escalate your privileges inside that pod. This would block that attempt. The second one is the validating admission webhook. And this is pretty cool. So with this one, you can actually, for every request of creating a pod, like in this case, that you see operation create of a pod, you can actually then reference a particular webhook that will then run some validation. So for example, are you pulling from the particular registry? Like in this case, are you pulling from my Azure Container Registry, or are you pulling from anywhere? And then if that condition is not met, that request is never going to hit the API server. It's going to be rejected immediately. Now in this case, that URL is actually sending you to an Azure function that in a serverless way is actually doing that validation. Normally you would run that piece of code inside, for example, a container and reference it here. I found it was a pretty good example of serverless use cases. So every time a pod is created, which is not always, it would trigger a function, it would run that validation, and then power down. Another very interesting webhook is the mutating webhook. So instead of just doing validation, this one can actually inject things into your request. So again, imagining that you're creating a pod, this one will be injecting a particular label that operations want to see visible in that pod. Another one, of course, is service account. Sometimes forgotten, but quite important. Service accounts, you don't want to just make sure that the users have permissions to do so. You want to make sure that the processes as well that contact the API have the right permissions and the granular permissions to do so. So you should definitely leverage service accounts to get those permissions very locked down and not just use the default service account. And coming soon, there are a couple more beta, very interesting admission controllers, things like node restriction that allows your kubelet to talk only to a specific node and to a specific set of pods, and things like pod security policies that basically set up a set of conditions that if not met by the pod in terms of security, so particular security conditions, that request will not be accepted. So it's in a way, it's similar to validating, but very focused on security. And these two will be coming to AKS soon. Now, we talked about the API server. Let's talk a bit about the VMs, the underlying infrastructure, actually. Now, AKS already provides you and no access to the masters, so you don't need to really worry about securing those. It's already secured by TLS certificates, by the managed service itself. But you still need to worry a bit about the nodes. And again, a cluster that is not up to date, that is not patched, is an insecure cluster. So you need to keep that up to date. You need to keep it maintained. You need to upgrade it. And ideally, you would do that monthly or in a minimum recommended time frame of 3 months. But that's normally quite hard because, I mean, you need to schedule maintenance windows, so on and so forth. And even with containers making things easier to patch the underlying host, it's sometimes still a bit cumbersome. Now, AKS, once more, tries to make things easy for you, and it applies patches, security patches, in a nightly schedule for you. You just need to worry about rebooting the nodes as required. And even then, you can use something like Cured to monitor the time when the nodes need to be rebooted, and it does it automatically for you. Now you might ask, what about the other updates, non-security updates, as well as the Kubernetes version? Well, once more, AKS to Rescue, it provides you with an extremely simple command that you can run. So normally it would be a very cumbersome process where you had to drain the nodes, cordon them, and then update them one by one, and make sure the whole process is secure, that your applications are not going to go down, that even your API server is not going to go down. AKS Upgrade will do all of that for you. You just need to choose the version that you want, and it will cordon, drain the nodes, and do the whole process for you. A note for you, you cannot update, you cannot skip minor versions. So you cannot go from Kubernetes 1.7 to Kubernetes 1.10 directly. You need to go 1.7, 1.8, 1.8, 1.9, and so on and so forth. What about SSH access? I think Mo already did a great job covering it. Of course, you could open your VMs to SSH access. I think everyone knows that's not really a good policy. You could run a container inside of the cluster and SSH to it. But then again, if you're running deny escalating exec, you really won't be able to do many administrative tasks. So really the best way is to use that jump box type of architecture. And lastly, to validate all of this, there are many tools out there like Kubebench, AquaHunter that you can leverage to actually validate your configuration. Let's move a bit to container, the container level. So the first thing you need to worry about when it's about containers is what the images that they're based upon. And of course, you need to make sure that they're coming from a trusted registry. They're not coming from anywhere. And you can validate that with that admission control that I just showed you. You need to make sure that they're updated as much as the hosts. You need to make a process in place. This is as much as a technical issue as it is an actual process issue. You need to make sure that you have a process in place to update them. But what about before they get into that trusted registry? After they are there, you assume that they're great for your cluster. Before they get to the trusted registry, you need to vet them. You need to scan them. And you need to make sure that they are trustworthy to be in that gold registry that you're going to use without restrictions. Except maybe one. You might want to make sure that the runtime, your containers that are running, are not changed or execute some unexpected task. So if someone goes into a container and suddenly decides to install a piece of software that is not vetted or validated, maybe it's exposed to some sort of CVE. So you can actually have runtime enforcement tools to help you there. So what this looks like in the overall spectrum of things is you would be developing, for example, in Visual Studio Code, using your dev cluster, maybe leveraging Draft, for example, to actually do debugging, troubleshooting, and then when you're happy with it, you're going to push to source control. At that moment, probably going to trigger some automatic build process. Maybe Azure Pipelines is going to pick that up, build an image, and try to push it to Azure Container Registry. Now that push is going to be subjected because Azure Container Registry integrates with tools like Aqua Security and Twistlock Container Security. You can integrate with those tools, and when that push happens, it's going to scan those images and look for CVEs that they might be exposed to, and make sure that they are according to your company's security policies. If they're not, that push is going to be rejected. If it is, it's going to be accepted, and you know that that image is trustworthy and it can be deployed in your cluster. And then to make sure, as I said before, that your containers are not going to do anything weird, you can also run some runtime security tooling. Again, Twistlock, Aqua provides some tools for that as well. NuVector also provides some cool tooling in that space as well. OK, so we checked the images. What about the access of the actual container? So the image is trustworthy, but what about if the container is compromised, for example? We need to make sure that it doesn't have privileged access so that then the attacker could actually compromise the whole cluster. So things like restrict the access to the IPC namespace or the PID namespace, which basically controls the visibility of the processes in the host and the communication between those processes. Is, for example, very important. Don't use and don't share those namespaces, because otherwise, if the container gets compromised, you can potentially see other processes within the host get compromised as well. Of course, avoid root of privilege. I think this is kind of one of the top of mind ones. Make sure that your containers, unless it's extremely necessary, don't run as root. And even when it's necessary, see, for example, Linux capabilities can take the cut. And you can just attribute very granularly a particular capability to that container instead of actually giving him root access altogether. So OK, those are some of the things that you can actually do. But there are many, many out there. So how can we actually get some help into creating a great container sandbox? So there are a couple of Linux kernel modules that will help you with that. AppArmor is one of them. It restricts a bit how some process functions will be done, and some system functions as well. So things like manipulating files, or for example, doing a mount operation can be restricted by AppArmor. It has a great default profile that you can load into your pods. So things like preventing a mount or preventing some network calls will be secured by AppArmor. If you want to make your own profile, you can very easily just write, in this case, a profile to deny every write to any file, so that if anything happens, that container cannot write anything to files. And then you load it into the pod by basically using an annotation with that specific profile. Now, what would happen in that case? I would try to do an exec into that container and try to, let's say, create a file. It would immediately get rejected. AppArmor is protecting that. Now, another a very interesting kernel module is seccomp, or secure computing with filters. And what does it filter? It filters system calls. Well, you can get much more granular than that. You can literally filter every system call out there. It, once again, has a very sane default profile that it basically will restrict around 44, if it's still the same system calls, out of 300 plus. So again, it restricts a lot, but it's still very sane. It won't crash anything. It will normally allow you to still run your workloads normally. And if you want to actually have your own, you can still follow the same idea and actually create your own profile and then annotate it into the pod. So if in this case, you try to create a pod, let's look at that pod just one more time. It's trying to do a change mod, which I'm preventing, and it's trying to do a change mod from 777. So when that pod runs and it immediately tries to do that change mod, looks like it's good, but when you actually list it, it actually errors out because seccomp is doing. Seccomp and AppArmor, although they don't totally overlap, they do overlap in some parts, and that actually is very, very good, because one of the best recommendations you can do is actually run multiple layers of security, normally 2, because if then one of them is compromised by an attacker, you still have another layer of security in front of your environment. So let's move really quickly to pod level. So the pods have a great mechanism to actually be able to very granularly define what you can and cannot do. The pod security context really defines that. So you can say, for example, that you don't allow privilege escalation. In that case, I'm providing with some specific Linux capabilities instead of actually giving root. I'm giving specifically netadmin and systime. And I'm even using SE-Linux labels in order to enforce a particular context, for example. Now, you might notice something interesting, which is I have 2 contexts, 2 blocks, yellow blocks there. That's because you can apply a security context to the pod, and you can apply it to each individual container that runs inside that pod. And you might even see something interesting, is that you have 2 run as user, and they actually are conflicting because one says 1,000 and one says 2,000. So by a show of hands, and also just to check if you're still with me, who thinks the processes within that container is going to run as user 1,000? Are you just afraid, or you just really know the answer? So it's actually going to run as 2,000 because the container security context is the one that's going to take precedence. So actually, it's going to run as 2,000, all right? So the next one is going to be pod security policies. We talked about them, that cluster level resources. That is going to basically validate if the pods are created against a set of conditions that you define here. So don't pay too much attention. This is a very restrictive policy out there. It's basically applying all those AppArmor and seccomp profiles. It's restricting the host IPC and PID namespace access, and it's doing a bunch more of validations there. If it doesn't, if the pod security security context does not match what is in this policy, the pod will not be created. And you can deploy this to the cluster, and it will be applied cluster-wide. So these are 2 very interesting ways to secure your pods. The next one that I would always recommend is make sure you use always pool for your images. Don't use the cached ones. Again, make sure, come back to that rule, always pull from your trusted registry. That's the single source of truth. You don't know what happened to that cached image, but you know that what is in that registry is trustworthy. So make sure that you always pull. You're going to get the latest and greatest image with the latest security features as well. Last part that I want to mention is really securing your workloads. So we've been talking about securing the pod, but what about the workloads? Imagine you want to access a database from within your pod. You normally use some sort of connection string that normally is leveraging the Kubernetes secret mechanism. That secret mechanism basically will hold that connection string and then will be mounted into the pod. Okay, so far so good. The issue here is that normally secrets are stored in etcd in plain text. So if your cluster is compromised in any way, those secrets can actually be exposed. That's kind of bad. So basically, Azure really has a way to help you manage those secrets, which is through Azure Key Vault. Azure Key Vault can help you secure the secrets in 2 ways. One, it will help you encrypt them. So it will store a key that will hash all those secrets in etcd, and it basically will be able to use that key to encrypt or decrypt. And 2, you will actually be able to store your secrets directly in Key Vault if you want, and then mount them as required. And I might be asking, okay, But how then will the pod access Key Vault to pull the secrets or to pull the actual key to the crypt? And that is by using something really, really cool, which is called a pod identity. So pod identities basically will allow you to create a particular identity for your pod, let's say an Azure ID identity, and then there will be a couple of components inside of your cluster, like a node, managed identity, and a controller as well, that will be responsible for mapping your pod IP into its identity that is pre-created by an administrator. I'm going to show that to you. So you're going to pre-create an identity, map it to that pod. Then once that pod, imagine, wants to access an Azure resource like Azure SQL Server that supports AD authentication, you're going to say, OK, I need to access Azure SQL Server. Those components right there, the NMI, is going to basically get that pod IP and match it with the identity that you pre-created and say, OK, AD, I need a token to access that database. And after that is done, you'll basically return that to the pod, and the pod will be able to securely access that. Okay? Let me just quickly show you that. Okay, maybe for the time's sake, I will pass to you, and you'll show some cool stuff. All right, let's go ahead with that.
Thank you. OK, that was intense. Let's get to some fun stuff. So what about auto-scaling applications and clusters? There are, manual scaling is tedious. You can't be sitting there and scaling pods, containers, and the underlying infrastructure. You got to depend on auto-scaling solutions. So there's horizontal pod auto-scaling, which is a Kubernetes concept that helps you scale pods and containers based upon CPU limits and other, custom metrics. Then there's cluster auto-scaling, that is scaling the underlying infrastructure. Guess what? When you are scaling pods, automatically, there might not be resources to place those pods. So you need to scale the underlying infrastructure. Or then you could use something that only Azure has, which is scaling with virtual kubelet or the ACI connector, which is instead of adding nodes to the AKS cluster, you just spin up ACI instances. So let's go ahead and take a look at how these work. Now, the horizontal pod autoscaler is fairly simple. It runs as a pod on your cluster. It's constantly talking to the metric server, collecting your metrics, and then at that point, when it notices that you've reached a threshold of CPU usage, it starts up another pod. Very simple. But that will work as long as you have resources to place these pods. What if the API server cannot place these pods? So let's go ahead and take a look at something called as cluster autoscaler. This is going to be available in AKS in a couple of weeks. But the way it works is it scales nodes based upon pending pods. So if the master API server tries to place a pod and there are no resources, the cluster autoscaler kicks in and starts up an additional node or as many nodes that are needed. What this does is it also reduces your dependency on manual monitoring, like sitting there literally waiting to add nodes because there is traffic, there is burst, so you don't need to do that. Let's just take a look at a demo that I have. In the interest of time and spotty internet, I've recorded this. So you can see that this is my cluster, and all I have there is a node pool with 2 nodes, and I've got here a virtual machine scale set with auto-scaling enabled. Auto-scaling is running as a master pod. It's is a component of the master, and the minimum count is 1, the max count is 4. So you can get up to 4, but never beyond that. So now what I'm going to do is going to take a look at the nodes and the pods. So if you see, I have now 2 nodes only. They are running. They got 1.10.6 version. I got a couple of applications running, a couple of Apache servers, and a load generator running. So let's see what kind of resources am I using in this cluster. So I'm going to take a look at the resources. You will notice that I'm using about 30-35% of the CPU in both nodes, and then you get a detail of if you do top nodes and top pods. So let's take a look at the autoscaler that we've deployed, the configuration of that. Now, take a look at this. This talks about the health of the cluster-wide health, because a Kubernetes cluster can have multiple node pools. That is why there is a cluster-wide health, and then there are node groups. And in this case, we have only 1 node group. So the first part talks about the health part talks about how many nodes are ready, how many are not ready, and how many were started, how many were long not started, how many of them have been registered, just to keep track of things. Then there is the last probe time. The last time there was a probe to figure out if there is a master API server trying to place a pod and doesn't have a resource. Then there is the last transition time. This is the time there was a scale up and scale down event the last time. And you get the same information for the node groups, which is our node that we have. We have only 2 that are in ready state right now. Now let's try to deploy an application. Very simple application. All I'm trying to do is basically try to create pods with limits set as 2 CPU and requests as 1 CPU. You would have noticed that my cluster doesn't have the resources. If I want to deploy 2 replicas, there are no resources. So I'm just going to try to deploy this. And then if I take a look at the pods that are running, I will notice that one of them was scheduled because there was resources, but the other one was not because I simply don't have the resources to place that. So let's go back and take a look at what's happening in the config map. If you see here, there's not much going on right now, no activity, it's not kicked in yet. It's still probing, it probes every 2 to 3 minutes or 5 minutes, whatever time you set up. So I'll place a watch on the nodes, get nodes. You'll see that very quickly, there's a node that has come up here. It's this node pool added, a third one, 0008. It was 20 seconds back. The other 2 nodes have been running for a day. So just to clarify, so a node was started a minute back to just basically place the pod that was in pending state. Now you can see that the config map has updated. There are 2 nodes, and the cloud provider target has been set to 3 now because I need 3 nodes. Now it will go through a process of adding that node to the cluster and making it available for the pod to be scheduled. There you go. We can see that it's all ready now. 3 nodes we have. And if we go and look at the pods, the nodes, it's up and running, get the pods, all the pods are running, so we're all good. So it's fairly straightforward. The scale down works simply, it waits for 10 minutes. If there are way too many resources, it marks one as a candidate to be here, as a candidate to be scaled down, and it does it. It doesn't do it as frequently as scale up because it doesn't want to scale up and scale down very frequently. So let's try to move on and talk about ACI connector. So now if you noticed, So if you noticed, the cluster autoscaler standing up a node actually takes a little bit of time. It takes a couple of minutes to stand up a node, and that might not be enough for you. If you have a burst workload and you need resources immediately, that might not be enough for you. So what you can do is you can use this concept of ACI connector that will allow you to spin just containers, as pods, and you can burst almost immediately without having to kind of scale your underlying infrastructure. On the left is the Kubernetes cluster. It has been maximized with all the pods deployed, and now we are deploying pods using the ACI connector. So whatever you see on the left is the ACI connector. Again, let me do a demo of this. So again, I'm just trying to show that I have one node in my cluster, and then I have nothing running on it. I'm going to deploy an application. It's a pretty straightforward, 3-tier application, web application. It's got a front end, it's got a back end, and a worker pod. The back end is a store that stores thousands of images. The processor processes these images and then basically reports the time it took to process images. And the front end is just a UI representation of all of this. So I've deployed the application, and then let's see if the pods are running. So we got all the pods running. Let's go look at the application. So you can see that this view represents a graph of the time taken to process every single image. Because I have only one node and one worker pod that I can deploy on that cluster, the processing speed will flatten out at 0.3. It can't go beyond that. So now what do? You have immediate burst. You can either choose to use the cluster autoscaler, or as I will demonstrate, you will use the ACI connector to kind of deploy the ACI connector and then spin ACI instances. So I'm going to install the ACI connector. You can see that the simple command that we have in the Azure CLI, we're going to make it available by default in the AKS cluster It's already been done, so you should have it available. So now, if you look at my nodes, I've registered, the ACI connector registers itself as a pod, and as a node, and also as a pod. The node is a representation that it's a virtual node, and it's actually scheduling pods. That's why it registers itself as a node. The pods, on the other hand, you will look, it is used as a like a label to allow ACI instances. So now what I'm going to do is I'm going to scale the worker nodes to process images faster. And I'm going to do that. I've deployed 5 copies of it, 5 replicas. And let's take a look at the pods now. They'll pretty much go into running state very quickly because there are pods. We're not starting infrastructure. But one thing to note is that we are reaching out to Azure to start ACI instances. This is not pods running locally. We're talking to the cloud provider to spin ACI instances. But it's still faster than standing up nodes. And once the pods are ready, if we go back to the UI, we will see that the processing speed has actually picked up. It's picked up quite a bit. It's 4 or 5 times now. And so the cool thing about this is you pay for the time, for only the time that the pods run. ACI is microsecond billing. You pay for the second that it runs. So that's that. What else? Number 5. So that's bursting with the ACI connector. Like I said, it's going to be added as a default in the AKS portal workthrough in the Azure portal. You can see that the virtual node preview is there. It's disabled by default. You can enable it. It's very straightforward. So moving on to high availability, multi-region high availability. Now your application is, for your application to be highly available, first there have to be multiple copies of your application, front end, back end, running on different nodes, so that if a node goes down, another copy is available. But it's as good as the underlying infrastructure. The infrastructure also has to be highly available. So most of our customers who run on production, they run this setting. So they run 2 identical Kubernetes cluster AKS clusters in 2 different regions, and these are paired regions like West US to US, West US, or East US to East US. So there are 2 identical clusters. The traffic first goes to the Azure Traffic Manager, and then it routes traffic to one or both of the clusters. So you can select weighted traffic, and you can send 99% of the traffic to one cluster, and then you can select 1% to go to the other cluster, and you can have probably one node there, minimal traffic going there. So this is great when one region goes down. That way, all the traffic can be routed to the second region, and if you have an autoscaler in there, it can just autoscale itself with the demand of the traffic that is coming in. This can also be used for cases where you have blue-green deployments, you're introducing new features. The new features can go into the secondary region, and you can test them out there. You can do any kinds of testing in there, and then when you're comfortable, you make that region live, and the first region then goes down, and then you can roll out the new changes there as well. So it's got multiple benefits. Most of our production customers run these settings. So we also have the Azure monitoring and logging running by default in the AKS clusters. It's important to always log everything to standard out and standard error. It's important to look at these metrics that we have. You can see that we have node CPU utilization, and I have plotted graphs selecting percentiles minimum and maximum. So that tells you, over a maximum period, how many resources are being used and how many at a minimum are being used. So that allows you to do capacity management. And then it also talks about how many nodes you have, then how much of the node memory is being utilized, the pod counts. So all of this is like a great view for the operator who is monitoring, for example, like a big cluster that is being used by multiple devs and multiple teams. Some of the other things that we have is we log node events. So you can basically go and query, and this is all integrated. If you go to the Azure portal, and if you click on the nodes here, and then you can directly get to the logs. And then you can see that when the node was created, it logged a bunch of stuff like that. It started the kubelet, it had enough memory, it had enough disk space, and then it started the kube proxy. It logged all of that. So if something goes wrong, you can see everything in the logs. When you go to the pod usage, You can see that I have a pod out here that is like hogging memory for 5 days. You can see that it's requesting, the requests are captured on the right tab. There's details around the CPU limit, the CPU usage, how much memory is being used. So all of that is captured. We also provide you access to customer control planes logs. These are master API logs, Kube controller, Kube API, Kube scheduler. You can choose to send them to Log Analytics, Event Hub, or a storage account. Just an example of that. Okay. And then we also have, so today you can only actually monitor one cluster, but we are opening up, allowing you to monitor multiple clusters. When you have a team, when you have a company that is having multiple, clusters given to different teams, and the ops guy wants to have a whole view of the entire, infrastructure, they can use the multi-cluster monitoring to monitor all clusters and view the usage. That's about it. Resources, we put in a bunch of resources that you can access here. This session was not like, could not capture everything because it's only 75 minutes. Each of these topic is, I believe, 2 hours in itself. So we've captured all the details in the first link. It's open source. Feel free to contribute. We'll be happy to take any contributions from you guys. And any feedback is welcome. Connect with us on Twitter. Thank you for your time, and I hope this was useful. Thanks so much.